Standard computers use bits, either 0 or 1. Quantum computers use qubits, which can exist as both at once. Through entanglement, they solve complex problems in...
Welcome to Module 2. In this video, we explore the Quantum Processing Unit, or QPU, covering its architecture, underlying modalities, and the microengineering required to create qubits. It's prepared by Dr. Qureshi from National University of Singapore, who is currently doing a project in the area of quantum computing hardware engineering. This video serves as an introduction to the QPU, the central engine that drives quantum computation. What is a QPU? It is a specialized coprocessor designed for quantum algorithms. Unlike a classical CPU, it requires extreme environmental isolation to manipulate delicate qubits. Comparing classical CPUs to QPUs reveals stark differences, from the fundamental units and processing methods to the extreme operating temperatures required for quantum hardware. The core mechanics of the QPU rely on three pillars: superposition, which allows for multiple states; entanglement, for instant correlation; and interference, to amplify correct outcomes. As noted in our hardware overview, a QPU is not just a faster processor. It represents a new engineering paradigm based on the fundamental laws of nature. Next, we will examine the various modalities and architectures used to physically engineer a quantum bit. Superconducting QPUs are currently the industry leader. They use microscopic circuits that exhibit zero resistance when cooled to millikelvin temperatures. The anatomy of these circuits includes the transmon as the actual qubit, readout resonators for non-destructive measurement, and interconnects for 2-qubit gates. Trapped ion processors use individual atoms suspended in a vacuum by electromagnetic fields. Lasers control these ions, providing exceptional coherence times and high fidelity. When comparing these, superconducting circuits offer faster gate speeds, while trapped ions provide longer coherence and better connectivity. Photonic QPUs use particles of light in optical circuits. Their ability to operate at room temperature makes them a promising candidate for scalable, networked quantum computing. Emerging modalities include neutral atom traps, spin qubits and quantum dots, and the theoretical topological approach, which offers immunity to local noise. Finally, we look inside the microchip to understand the importance of topology and nanoscale precision in hardware design. Qubit topology defines how qubits interact on a chip. Non-adjacent interactions require swap gates, which can introduce latency and potential errors into quantum algorithms. At the atomic level, superconducting qubits rely on the Josephson junction. This insulator, often only 1 nanometer thick, is critical. Any imperfection here significantly degrades the qubit's coherence time. On-chip elements are essential for control. Qubit pads govern frequency. Tunable couplers manage entanglement between neighbors, and drive lines deliver the precise microwave pulses needed for operation. How do we measure the efficacy of a QPU? Evaluating its power requires looking at specific performance metrics, which we will examine next. Key metrics include qubit count for raw capacity, coherence time for the duration of a quantum state, and gate fidelity, which measures the accuracy of individual operations. Quantum volume aggregates these factors into a single metric. As error rates decrease, quantum volume scales exponentially, indicating a processor capable of executing more complex and deeper circuits. Achieving 99.9% gate fidelity is a vital milestone. Crossing this error threshold is essential for the mathematical possibility of quantum error correction. Beyond design, the physical fabrication and the operating environment are just as critical to the functionality of the quantum core. Quantum processors are manufactured in clean rooms using specialized materials. Because even microscopic defects can destroy coherence, extreme precision is required throughout the fabrication process. The environment is equally demanding. A QPU must operate at roughly 15 millikelvin inside a dilution refrigerator to protect the delicate quantum states from thermal energy. Looking ahead, we must address significant engineering challenges on the road toward fully fault-tolerant quantum computation. Decoherence remains a primary obstacle. System noise, magnetic interference, cosmic rays, and signal crosstalk can all compromise the information held on a quantum chip. We distinguish between physical qubits, which are noisy and hardware-bound, and logical qubits. Logical qubits are stabilized entities formed by groups of physical qubits using error correction. Scaling requires modular architectures. Future systems will likely transition from single-chip designs to interconnected arrays of QPUs, utilizing high-speed microwave or optical links. The final goal is the fault-tolerant era, where massive arrays of logical qubits will enable us to simulate complex molecules and solve previously intractable optimization problems. Thank you for joining this exploration of QPU architecture. We hope this provides a clear understanding of the engineering required to build the future of computing. If you are interested in exploring research collaborations, pilot designs, or technical training, please feel free to reach out via email or connect through the professional networks listed here.